Okay, well, I got the feeling maybe I was rushing through this. It's just starting to move away from any concrete understanding of this, and it just looks like a bunch of letters. I don't want that. So what I was thinking, yeah, let's just, rather than do the proof of this, which isn't hard at all, we will just let's look at a little example. So suppose let's use the dice again. So you should get used to the idea that there are 36 outcomes in the dice and that they can take on, that they're ordered. So you really have, this is a good representation of S so that's S for dice, right? And maybe down here, this is one of the die and here's the other die. Okay, so 1 through 6. Okay, 1. All right. So for example, if I want this to be the first die and I want to say 2, 3, that would be here, right? So something like that. Okay, so let's look at this EF union, this one here, and just see what happens. So if E, let E again be, what did we say? Sum greater than or equal to 10. And when you're writing in English, you don't have to write the curly brackets. And F, let's say F is doubled. You can if you want, if you like it. F is doubled. And what about G? So GB. G is second die is 6, say. So this is this. So yes, so we can, in a way, we can draw a picture of each of these and do it graphically, more or less. Second die is 6. Let me do G here is like this, right? This is G. I don't want to clutter the drawing, but that's G. If I had different colors. Doubles, same of each, right? So 1, 1, 2, 2. So doubles is like this. And they're gonna overlap a little now. So it's gonna be a little confusing, but, and sum greater than 10, well that's this one, this one, this one, this one, this one, this one. So now you can't really tell. You can see the union of all three. That's the union of all three of them, is all that's shaded in. But otherwise, it's not so clear what's what. But let's just verify the distributive property there. So verify. And remember, this distributive works this way when you taking the like multiplication and addition, right? Not the other way. So we'll verify E intersect F union G is equal to EF union EG just by doing the calculations. Okay, so what's EF? I don't know why I want to start with that. Which sums that are greater than or equal to 10 are also doubles? So this would just be 5, 5 and 6, 6, right? Has to be both in both of them. Okay, what about EG? Sum greater than 10, second die is 6. Greater than or equal to 10, second die is 6. So this is just, this has 3, 4, 6, 5, 6, and 6, 6. Okay. So EF union EG then is anything that's in either of them, and it's just EG. This gives me nothing new, so I add the 5, 5 to EG. So 4, 6, 5, 5, 5, 6, and 6, 6. Okay, now let's check the other. You see, this is a little time consuming. Now let's check the other one. So what's F union G? It's going to be big, right? F union G. So I like doing it this way better. The first way seems better. So F union G is anything that's doubles or the second die is 6. So that's this and this, right? So that's going to have 11 elements in it if I write it out. So let's see. Can I avoid it? 1, 1, 2, 2. You get the idea, right? Dot, dot, dot. 6, 6. So all the doubles. And then I gotta keep going. 1, 6. 2, 6. Dot, dot, dot. 5, 6. All the ones in this column. Okay, so if this was just notes, it would probably be confusing, but it's okay. You can will follow it because I'm probably going to use this sheet for the notes too. Okay, so and now I want E intersect F union G. So E is all the ones where the sum is greater than or equal to 10 out of here. Okay, well, in here the doubles gives me 5, 5, 6, 6. And in this one, this gives me, let's see, all the one with says 4, 6, 5, 6. So you see, it's the same. It's these four. So E intersect F union G has to be in both, right? So E sum greater than 10. F union G is this. So F union G is this, and now I look which ones in this and this are in this little triangle here, and the answer is this one and then these three. So the answer is that one, 5, 5, and then 4, 6, 5, 6, 6, 6. I can make a little picture of this. It's just, if I have this, it's just these three, right? And this one. Okay. All right. We have also now, so that took some time, but it's okay. We have a fancy law called the Morgan's Law. Useful. Which says that complement of a union is the intersection of the complements. And same thing with complement of the intersection, so I'll write laws, is equal to the union of the complements. Easy to remember. Okay, easy to remember. So, so these I can do a little proof. I could do a little proof. This actually extends to E union F. This actually extends to any number, even an uncountable number. Even an countable but infinite set, I can apply this to. So, so we can extend it. So it can be extended to, if I want, let's say I have the union of EI, and I take the complement, say 1 to infinity. This is equal to what? Well, the intersection of all of them, right? So this, we usually just write, well, I guess I could just do it like this. E1 complement, E2 complement, right? It's the intersection of the complements, dot, dot, dot. For okay. So extended to countable sets. All right, let's do a little proof. Let's see how much time we have. 9 minutes. So let's do a proof of one. So proof, let's prove of, say, E union F, C equals EC FC. Okay, so let's prove this one. Okay, so I just do this by showing one set is contained in the other and vice versa. So maybe I'll only even do one direction because we're running out of time. So to show two sets are equal, show A is contained in B and B is contained in A. Okay, so that's what we have to do. Okay, so I'll show, so the way to do this is you pick an arbitrary outcome in one and show that implies it's in the other, and then you've showed one is contained in the other. So let's let little s be contained in E union FC. Then we'll show it's in ECFC. Okay, so then what does that mean? S is not in E union F. That's the definition of C, right? So if it's not in the union, then it's not in either. So F is not in E. And S is not in F. Because if it were in one or the other, it would be in E union F. So S is in EC and S is in FC. So finally, S is in ECFC. So we just showed, this shows showing that E union FC is a subset of ECFC. Okay, because I just showed that anything in E union FC is in ECFC. Okay, so it's similar. I won't do it. It's similar to show, you should do it. ECFC is contained in E union FC. And then, so that's the proof. Okay. All right, yeah, I gotta stop. We will definitely be using De Morgan's laws, some of these laws, in some of the problems we're doing coming up. The very next thing is the axioms and the definition of probability. So thank you. Check out the next video.